On the cloud. Cool, we're recording. All right, hi everybody, welcome to Python Club, part 6 of Back to Basics. I hope everyone has had a good week. And am I screen sharing yet? No. Okay, now I am. Cool. I was trying to think of something funny to call this. I settled on greatest hits because it rhymes. So let's have a quick recap of what we've been up to. So in the last couple of tutorials, we downloaded a PDB file from the internet using, I think it was our bash commands. Then we extracted the coordinates of each atom from the protein. We used a KD tree algorithm from SciPy to find the distance between atoms that are less than 10 angstroms from each other. Angstroms is the unit of distance that we're dealing with here. And we made a graph of the structure using NetworkX, where a graph is a data structure that has nodes and edges or links. Like for example, a network, like the London Underground, for example, the internet, or molecules in our case, where each node is an atom and each bond is one of these edges or links. And we added some attributes to each of these nodes. So let me scroll up a little bit. Here we go. So here's some of our graph of some of the bonds. It's being drawn not chemically. The algorithm that draws it here is just trying to keep all of the nodes as far away from each other as possible so that it looks vaguely sensible. So you'd have to use a little bit of imagination to try and figure out what sort of compound it is. Sorry, fine. And then we set some attributes like this for each of the nodes in the graph. Remember that one because that's going to come in handy later. Hi, Steve. So this time we're going to have a little look at some of the attributes of the NetworkX graph object, NetworkX being the name of the library that we're dealing with. We're going to scratch the surface on graph algorithms. I think I had add plans, but I haven't had enough time to implement them. So maybe next time then we'll do some more interesting graph stuff, which should be pretty cool. And very briefly, we'll start looking at objects and using class to create our own custom objects and so on. Okay, so let's take the graph object that we created in the last tutorial. So down here, we're dealing with this object, G short bonds. Let me paste that into a new cell up here so we can have a little look at what we've got. Okay, so that's its location in memory and a little bit of information about what type of object it is. So you remember that the G short bonds is all of the atoms with the element symbol for each one, and and each atom is linked to any other atom that we thought was between 1 and 2 angstroms within each other. And we're, for now, just going to assume that that is a covalent bond. We're ignoring whether or not it's like a single or a double bond or whatever, because we want to keep things simple. So that's the object that we're dealing with. Let me bin this cell. See you later. Okay. And let's have a little look at some of the attributes of the NetworkX object. So the NetworkX object has like a fair few attributes, and this instance of it, G short bonds, well, the main attributes are nodes and edges, edges being the name for the links, and in our case, nodes are atoms. So we'll print some of those and have a look what they look like. So in this statement, we're looking at the first node, and you can see it returns a dictionary with the attribute that we added to it in the last tutorial. And we'll also look at some of the edges here. Why did I bring this up? I think it's partly because later on I'm going to start talking about objects and the attributes that they have and the methods that they have. Methods being like a function that belongs to an object. So as well as these attributes, which is like stored data, I suppose, these objects also have built-in functions. So For example, we have a function here for adding nodes, removing nodes, and when we print that without the parentheses and an argument or whatever we normally put in, again, we get information about where it's stored in memory and so on. So as well as adding and removing nodes, we have some slightly more interesting functions that are associated with each one, particularly neighbors. So calling .neighbors and then feeding the index, like 1, 2, 3 or whatever, will return the indices of all of the atoms that neighbor that atom, or all of the nodes that neighbor that nodes, for a more general description. It returns an iterator. How do I know that? Well, when we run this function here, it returns a dict key iterator. And normally when I see iterator, my go-to is normally to use the list function to sort of unpack it. So on the next line down here, that's what I've done, list, and I've just fed it the same argument as before. What does that return? It returns a list of the indices of the nodes that are neighboring node number 1. And then to find out the identity of each of those nodes, what I've done here is I've chosen to loop through this list of neighbors that I've unpacked. Although, you know, this might be sufficient as well because we're already iterating through it. Yeah, the list part of it wasn't, strictly speaking, necessary. So for each of these numbers in the neighborhood of atom number 1, we will call it, we can get information about that particular node. So that's what we do here. So we look it up just like we would a dictionary. So within the graph object, we have the nodes attribute, and we can look up a node by its index. So in this case, I will be like I equals 0, then 2, then 4. So G short bonds nodes I. Let me put that in another cell, show you what's going on. Okay. So I haven't actually defined I yet, I don't think, but yeah, it will return you a dictionary with the attributes of each particular one. You'll notice that in my notebook, I've got atom type because I was working on this notebook. I skipped ahead basically, but yeah, best ignore that for now. Okay, so we've had a little look at some of the attributes and some of the functions or methods associated with the NetworkX graph. And now we'll dive straight into an exercise where we're going to put some of that into practice. So you might have noticed that in the PDB file that we looked at, when we extracted the atom coordinates and so on as a data frame, there were these atom types as well as the element symbol, which would be, you know, like C for carbon, N for nitrogen, and so on. We also have Ca, which I know stands for carbon alpha, and Cb, which stands for carbon beta. So that's a notation for, it provides information about what the role of that particular atom is in the protein. And I want to use a neighborhood search to sort of confirm my suspicion that the identity of the atom is in large part determined by its neighbors. So the pattern that we're looking for is we want to see what neighborhood of each atom corresponds to each atom identity. So the aim of the exercise is to for each atom, we want to have a compare of, we want to have a compare of the atom identity that we see here, side by side with a list of the elements that are neighboring that particular atom. That's the aim of the exercise. So let's break it down into a couple short parts. So number 1, I guess we'll be wanting to loop through all of the nodes and then set a new attribute to each of those nodes. So the attribute that you should already have is the element symbol, but we also want to add to it whether or not it's a alpha carbon or OG1 or whatever. So that's part one of the exercise. Then part two, we want to find the neighbors of each of those atoms and get the sort of the raw element symbol so that we can actually start to compare these things. So yeah, part two will be then loop through all of the nodes, which should now have both the raw element symbol and the atom type associated with it. And well, you can store the data how you like, but I chose to store it as a list of dictionaries because that's what I felt like doing. And then after that, then we can print the results to inspect them visually and try and pick out patterns the old-fashioned way. So I've left a cell for you here. Feel free to ask any questions, and I will start a timer for 5 minutes. And whilst that's running, I am going to start delving into classic art, I think, because I think I should try and avoid using unlicensed music whilst I'm waiting for an exercise to run. So instead, I'm gonna draw the Mona Lisa in Paint because I feel like it. If anyone has any questions, feel free to ask either out loud or in the chat. I might see the chat. Yeah, let me bring it up. Okay, that's this black box here. Oh, why not? That doesn't look very good. Perfect. Okay. I hope the exercise went well for everybody. The Mona Lisa definitely went. The Hunchback Mona Lisa. Steve. Yeah, she is. Yeah. Well, at least I've saved it. Maybe next I'll do the screen. Okay, where are we? So in the cell below, I've pasted the answer that I've imported from the supporting file, which I'm going to bring up because, to be honest, I was pretty focused on drawing the Mona Lisa, so I'll co-pilot myself with my own old functions. Okay, this is going to be a bit of a tricky one, isn't it? Part one, look through all of the short bonds and data frame atom types. Well, I'm looping through two things, so I guess that means I'm going to use the zip function to loop through multiple things. So let's go for I, J. Should we call it I or J or something more informative? Nope, I and J. And what am I looping through? The data frame atom type and graph dot nodes. Cool. G dot nodes. And df atom type. Does that work? Have I spelled something wrong? Yes. Invalid syntax. What have I done here? Good question. Well, I'm gonna print in the cell above. Okay, so the atom type was spelled correctly. And g.nodes is spelled correctly. Maybe it doesn't like the pass statement. IJ in. Okay, for IJ in both of these objects. And what am I doing? Okay, so I'm setting a attribute to each node. So as I loop through, I will be equal to the node index and J will be equal to the atom type. And just like you would if you were setting a value in a dictionary, you access the value that doesn't yet exist. So g.node I, let's print that actually, see what that looks like. So you might remember from earlier, it printed something a little bit like a dictionary, which is empty, that's fine. And just like you would set a dictionary value, we're creating a new key, atom type, and setting that equal to J. So now let's have a look at g.nodes, see what that looks like now. Cool. Okay, that's not very informative. How about let's look at the 0th node and see what that looks like. There we go. Atom type is N. So it's just struck me that I've been using this variable G, and actually what we want to be working through is G.short bonds. Can I remember the difference between G and G.short bonds? No. Okay, so in this loop we have set a atom type to each of the nodes. So that's exciting. That's part 1 done. Now loop through G short bonds and get the atom type of each element. Yeah, this one was a little bit of a tricky one to make actually. So I'm gonna, in the interest of time and making life easy for myself, I will refer to my cheat sheet answers. So let's have a little breakdown of what I'm doing here. Well, here I've got a loop within another loop, and it seems to be dumping everything into this list that's outside of both the loops. So I create an empty list, and then I start looping through all of these nodes. I create a variable called atom type. So let's put this in and see what it does. Put you over there. Let's print atom type. See what that looks like. Okay. And then it comes to actually finding the neighbors of each atom. So you can see here that I've created a imaginatively named variable called neighbors, which is equal to g.neighbors. Yeah, you know what I need to do again. So in the function, I was using g as a placeholder, which is fine in the function, but I also have another variable in this notebook called g, so that's what's leading to confusions. Okay, so I get the neighbors for each atom as I loop through it. So let's have a little look at neighbors for each one. Wow, that's a lot. Okay, fantastic. And if we wanted to unpack that to look a little closer, we could unpack it by calling the list function around it. Here we go. So we can see some atoms have no neighbors for them, and some of them have plenty of neighbors. And they're all accessed by, or sorry, they're all identified by this one number. So what do I do with that number? Well, it looks like I'm using it to, again, go through the graph and then extract the element type for each one. So what have I done here? I've made an empty list again. So I suppose I'll do what past James did. Equals empty list for j in neighbors. What have I done? And we'll remember that neighbors looks a little bit a little bit like that. So what do I do now? Okay, so now I'm trying to access the actual element number. So I guess then we can look at the nodes attribute of this object and then look it up by j. So let's print that out and see what that looks like. Okay, so as I loop through, I'm getting a dictionary that contains the element and the atom type, and I am interested in the element, I think. Somewhere right here. Yes. Okay, cool. So now we have the atom identity of each one. So I guess then we'll be appending it to this temporary list that I've made. Let's have a look at that, see what it looks like for each one. Okay, cool. So now we'll print I as well. Why not? So we have the index of each atom, and then we have a list that contains the element that corresponds to its neighbors, its covalent neighbors. Fantastic. Well done here. Okay. And then what it looks like as I've done is created a new. Yeah, I see. So then with this list that I've just made, so now neighboring elements contains will look something like that. I then append that to the list, the empty list that I made outside of the loop, and I've chosen to add a dictionary to the list each time. So let's have a little look at what that creates. Okay, what about on here? Neighboring elements is not defined. Yeah, I think that looks like a spelling error. There we go. Okay, so now this atom types n neighbors is a very, very long list that contains the atom identity as the key to the dictionary, and then the values of that dictionary are then a list containing the element ID of its neighbors. Okay, so now we're sort of halfway there to finding a pattern between how the atom identity corresponds to its neighborhood. So let's dive a little bit deeper in there. So we have a quite a long list here, and ideally I'd quite like to remove all of the repeated elements. So in the cell below, I import the function that I was cheating off earlier. If you want to find the cheat file, then you can find it on our GitHub. Within the tutorials folder, there will be a back to basics.py, and that is this. So yeah, in each step, I'm just importing one of the functions individually. Okay, so I define this this variable called neighborhoods, spelled wrong, but we'll roll with it. Doing pretty much exactly this. And then I print the first 5 or so elements of it. Come in. Okay, now we want to find the unique elements. So the way that I'd be inclined to find unique elements of, say, a list. Say I've got 1, 1, 1, 1, 1, 2, 3, 4, 5. Sure. Okay, so I've got this list. So typically I'd be using something like the set function to find all unique items in there. That's one way of doing it. But set won't work on our neighborhoods, or at least it didn't whilst I was trying to make this tutorial. I don't think it likes the idea of comparing dictionaries to dictionaries. Just a bit of a bummer. Okay, so let's move on to exercise 6.2. So using this object neighborhoods, or if you defined your own in exercise 6.1, then feel free to use that. The aim of the exercise is to extract all unique items from that list. There are probably multiple ways to do it, so feel free to do it how you want. I'll set a short-ish timer for maybe, I'm gonna say, yeah, I'll just do 4 minutes, why not? Okay, off you go, and then in the meantime, I'll be drawing Screen by Edward, I think he's called Munch, something like that. There we go. On a note of the exercise 6.2, the way that I ended up doing it and the answer that I'll be showing is based on looping through and then using an if statement to say if this item isn't already in whatever container I'm putting it in, then put it in. If not, just leave it. That's the gist of my function. Hands are always difficult to draw. That's his V-neck. Yeah, doing an exercise, drawing the screen by Edward Monk. Perfect. Oh no, that's not good.
So good.
Thanks. All right, now for some perspective.
There's some color in it.
I'll do the color at the end. I don't want to dive into.
That's true.
You can't rush art.
Oh, you're doing that.
Yeah, doing the boardwalk.
You're doing the wrong profession, yeah.
Yeah, why do I do code? Should have been an artist. I mean,
You are.
I am. Yo. Thanks. I'm an artist. Oh no. I'm doing time. Oh my god, 30 seconds, you know what that means. I think I just got so absorbed in drawing this that I just completely forgot that I'm supposed to be hosting Python Club, but yeah. Okay, so where did we get to? Yeah, exercise 6.2, fantastic. Okay, yeah, so we're working with this object called neighborhoods. So that's a list of dictionaries, and we want to find the unique elements in it. Having found out that doing the easy way, set, doesn't quite work because of dictionaries, we are instead going to go for well, I'm gonna do a loop. So what am I going to do? I'm going to make an empty list called unique atoms. Sure. At some point I'm going to get better at naming my variables, but for now I'm just going to do this. And now I'm going to start looping through this neighborhoods object for I neighborhoods. What does each object look like, or each item? Let's have a look. Print I. Ah, yeah. Okay. So it's a dictionary that contains a list. I remember now. So I suppose I want an if statement. If I is not in unique atoms, come on, autocomplete. Never mind. Then unique atoms append I. Okay. And let's have a little look at what that returns us. Okay, well, that's looking a little bit more like it. So, I mean, it's quite a long list. It's a very long list. But do we have any repeats? Well, I've seen a couple of repeats. I've seen quite a lot of O. And then down here, there's more O's. Loads of O's. Why is that? Well, in the crystal structure that we've been looking at, there is water that surrounds the protein. That's just how the image was taken. And the O that we're looking at here is the oxygen from those waters in a lot of cases. Why isn't it bonded to an H? Well, it's because H's, hydrogens, are a little bit too small to image using crystallography. Please don't tell a real crystallographer that I said this, because I've probably made a real hash at explaining it, but that accounts for most of these O's that we see that have pretty strange neighborhoods. Although that being said, looking at their neighborhoods, it seems like they are within what I assumed was covalent bonding distance of quite a lot of atoms. So I suppose it highlights one of the drawbacks in the way that we've been describing our bonds by purely based on distance. But oh well. Okay, well let's filter out all of these O's as well. Why not? As we print it out. So in the cell below, I think I did exactly that. Yeah, okay, so I've made pretty much the same object in the cell below. I import this function, find unique neighboring atoms, which looks like this. So just like in the example that I took you through, I create an empty list called uniques, and then for each item in the neighborhoods, if that item is not already in the output list uniques, then we'll add it to it and then return the list. Okay, cool. So uniques should probably be the same as unique atoms, which I created in the cell above. So we'll have a little test of that. Unique atoms. True. Okay. So we've got the same answer. That's good. That's reassuring. So if I don't want to see these O's, then I can. Well, what I've done here is that I've looped through uniques in a print statement, and I say that if capital O is not the key of the dictionary, then print it. Let's get rid of this small slice so we can see all of it. What have I done? Have I gone up a cell? I'm getting lost in my own notebook, you know. Okay, I hid the cells for myself. Fantastic. Okay, so now we have all of the unique elements, apart from all of those pesky oxygens, presumably waters, that I mentioned earlier. You'll notice that a lot of these objects do indeed contain O's, and I say if O is not in that particular item of the list, then don't print it. So in this case, we can assume that the O or the statement only applies to the dictionary keys. Okay, let's have a little look at what we've got. So there's quite a lot of different atom types here. Well, initially we've got an N and then another N with a slightly different environment. So that's a bit of a red flag. Why is that? Well, at the start of the protein, there is a nitrogen that is assigned the name N that is in a slightly different environment to all of the other N's that are in the main chain. And the reason for that is the rest of the nitrogens are mid-chain as opposed to start of the chain. The same is also true for one of these carbons, which might be, I'm not sure which carbon it is. Maybe carbon beta. What do you reckon? Who knows? That's right. So, well, at least we succeeded in finding all of the unique elements. We can see that there's quite a lot of atoms that do have the same environment, but yet have a slightly different name. Why might that be? Well, they might be in a slightly different position in the chain, and the way that we can find that out is by looking at their neighbors, and that's where we'll probably start to see differences. Okay, so over the course of this exercise, I've been trying to show that these atom identities that we have here are at least in part determined by the neighborhood that the atoms are in, and I think I succeeded in a less than convincing explanation. Fantastic. Okay, let's take a break from graphs for just a little bit. But don't worry, we will come back to graphs because there's a lot to cover. For example, in the NetworkX package, we have plenty of algorithms for clustering, finding the shortest paths, looking for substructures, and many more. Look at this link for examples of what else. If you just can't wait to find out more about NetworkX graph theory and things that you can do with it, then follow this link to the documentation. And if you want to look under the hood of what's going on in NetworkX, then check out the NetworkX GitHub to see exactly how all of the objects work. Earlier on, I downloaded the NetworkX library and had a little look inside it. So let's open up one of these files, graph.py. So these are the objects under the, or this is what it looks like under the hood that we're working with. So the NetworkX graph looks like this, and you'll notice that in the file itself that we're working with, I mean, there's nothing magic about what's happening. It's another Python file with an object designated by class and then the name of the object. And luckily, NetworkX has loads of what are called doc strings, documentation strings. That's this. It's a multi-line string designated by the triple quotes with loads of information of what you can do with it. So I suppose a take home from that is that if you ever get pretty lost with the code that you're working with, or if it's poorly documented, then you can have a little look under the hood for some help. And you might also notice that a lot of these objects have this function with a double underscore init, which is short for initialize, and then another double underscore. And this is the function that is called when you initially make the object. And you'll find that under the hood, it's setting a lot of attributes for you with that object. So let's talk a little bit more about object, because over the course of Python Club, I haven't really taught that much about objects, but pretty much everything is an object in Python, or at least I think I heard someone say that once, and I gave up trying to fact check that pretty quickly when I was making this tutorial earlier. Sorry about that. So let's talk briefly about objects. Broadly, according to the Wikipedia page under this link, it's a variable in memory with a name. Nice spelling there, James. And in Python, it's an instance of a class. So I just showed you the class for graph that we're working with in NetworkX. And you can think of the class as a template for an object. Other objects that we worked with in the past are stuff like the pandas data frame, but even small things like, for example, strings and integers and so on are their own objects. And under the hood, you might see something a little bit like this for each one. Okay, so in Python, I guess two things to be aware of with objects are each object has methods and attributes. So earlier on, I was showing some NetworkX graph objects which have methods, that is functions that are sort of belong to that object. Like for example, add node in our NetworkX object, and then it also has attributes, which is like data that has been stored as part of that object. So in short, a object in Python is a thing that has data associated with it. It remembers data and it has functions, or at least it can have those. So short of actually setting an exercise in this bit, this was all pretty last minute, but I'll show you, I'll make an object and show you what's going on. And then in future tutorials, we'll use this knowledge to create a object specifically for the protein that we're working with. And it might contain, for example, the coordinates, the graph, and maybe some useful functions to sort of bundle everything together and make everything a little bit easier. So the way to make a template for an object in Python is with class. It's probably most similar to the define function, def, that you're probably familiar with. The only difference is that it's for defining objects, like I mentioned. So I define this object called a test class. No parentheses needed here, although parentheses can be put in some cases, but I'll get onto how and why another time. So this object has functions associated with it. It doesn't yet have any data, and I'll get onto storing data in an object in just a little bit. But you'll notice that within this class object, under the indents, I define more functions where I'm just printing emojis, for example. The utility of this is if you want to sort of group functions together or bundle them or something like that for helping yourself keep track of things, then this is a perfectly viable way to do it. So you'll notice that I can run functions like this, but it doesn't save any data. I've not initialized an object. I've just got really a sort of a fancy way of bundling functions together. I've not really done anything particularly useful. Particularly useful. I've not stored any data. So in the last couple of minutes, I'll show you how to store data. So I make another class, same as before, I give it a name. And crucially, I provide the class with a init function. You might remember init from just earlier on where we had init, which we saw in the NetworkX package. This is fairly common. I'll get onto in the next tutorial what these double underscores actually mean. But for now, all you need to know is that this function, the initialize function, is called when you make an object like this. So just like running a function, I follow it with parentheses. And in some cases, you might want to initialize the object with some data. So what have I done here? So in this case, I'm going to feed it the parameter 2. Why not? And now this object x has x.x. I really should have thought of a better name for this. So when we run this function up here initially, or sort of initialize the class here, this function is run, and the self that I keep on referring to is sort of like saving the data to that particular object. And again, in the next tutorial, I'll explain what on earth self actually is. But if you want anything to be remembered within these classes that you're making, then you'll have to make a lot of references to self. And then I can access items within that class by this sort of like hierarchical accessing x.data, for example, and then I'm accessing this little emoji of a parcel. Okay, so I've got more to say about classes, but I'm going to say it all next week, where hopefully we will be creating classes to represent the protein data that we've been working with so far, and hopefully we can build in some useful functions that we can use for that sort of thing. And then we can use that template for creating objects from other similar PDB files. And then maybe we can use some network X algorithms to sort of make substructure comparisons or something like that. I'll think of something in the week. That's all I've got for today. If you have any questions, then please let me know. And if anyone wants prints of my artwork, then let me know. I'll print it out at work here and send it in the post. All right. Any questions? No. Okay. Well, lovely to see you all, and I'll see you all next week.
Cheers, James.
Cheers,
See you
James.
later.
Thank you.
Thanks, guys. I'll see you later.